Our final presentation is an in-depth study analysis on case study of slope failures at Spilman Islands, presented by Miguel,
Zifa, and Mary.
So to start with some background and introduction, Spilman Islands is a dredge disposal site located in the Houston-Galveston Ship Channel. So what is a dredge disposal site? A dredge disposal site is an area allocated for land disposal of materials dredged from wharves, navigation channels, and major shipping lanes. So what are some of the components underneath the Spilman Islands of the soil? So the Spilman Islands is sitting on top of deeply eroded clay that occurred after the final glaciation period. So these soils that form are generally stiff to very stiff, over-consolidated clay, varying between red, yellow, and brown in color. We also know that levees are often constructed on top of previously dredged sediment soils, and we know that these soils are typically very low in strength. And if the rate of levee raising does not allow for these sediments to consolidate and gain additional strength, overall slope instability could occur. So this case presents the results that using stress history to predict stability conditions of raised levees is accurate. Now for the description of the failures that occurred in the levees in the Spilman Islands. So first we can trace all the cause of failures back to 1982, when the South Levee was removed and reconstructed over existing soft dredge sediments. We know that at this point the levee crown was at an elevation of 6 meters mean low tide, which is a level of reference. By 1988, the levee had approximately settled to 5 meters. So we know in 1989, when the levee was had attempts to be raised to 7.3 meters, and in 1993, these attempts were made to even higher, to 9.8 meters. So we know that in 1993, when the levee crown reached 8.5 meters, the dredging contractor noticed that there was a bulge on the exterior toe of the levee, and there was also observations of cracks in the levee crown. There was a 2-meter thick berm constructed to keep the exterior of the toe from bulging, and construction continued to 9.8 meters, and at 8.5 meters the second slope failure occurred. And after this failure, the engineers decided that they would place a geotextile fabric layers at elevations of 6.1 and 6.4. After this, the construction continued and planned to be at a level of 9.2, and in 1993, as the crown reached to a level of 8.5 meters, another crack occurred in the levee crown. All construction was paused until 1995, where the crown was successfully raised to a level of 9.8 meters above mean low tide. This elevation was selected to match the present elevation of adjacent perimeter levees in the preparation for future dredging operations.
Okay, so now we're going to look at soil properties and lab test results. The test results showed two distinct soil layers. The first was the clay-fill soil layer, which established the levees, and the underlying dredge sediments layer. So here we have figure 5, which shows the liquid limit versus the plasticity index. Both soils classified as type CH, clay high plasticity. The dredge sediments had a higher plasticity index values than the clay-fill soil. 100% of the dredge sediment passed the number 200 sieve openings, but only 65 to 85% of the clay-fill soil passed the number 200 sieve. The index properties varied due to soil origins. So the clay-fill soil came from hydraulic fill material, which is over-consolidated clay that was loosely compacted. The dredge sediments layer came from dredge maintenance material, which is very soft, fine-grained soil. So here we have figure 6, which shows the index and shear strength properties. The clay soil liquidity index was generally less than 0.3. The dredge sediment liquidity index was generally greater than 0.5. The moisture content and shear strength of the clay soil did not vary with depth, but the moisture content and shear strength of the dredged sediment did vary with depth. Also, the total unit weight of clay was greater than the total unit weight of dredged sediment. So the 1993 slope failure analysis approach was the following. The shear strength and the time rate gain were back calculated, then the observed and the computed stability conditions were compared. And so if this data predicted the failure, then it was reliable and it could be used for future levee raising. A 2-dimensional limiting equilibrium slope stability program for a non-circular shear failure surface was used. For the clay fill soil, the shear strength profile was used to estimate the undrained shear strength parameters. And we could do this, or they could do this because the undrained shear strength was constant with depth. For the dredged sediment, the undrained shear strength depended on two things. The initial undrained shear strength, which was affected by the thickness of the topsoil, and the over-consolidation effect of tidal action. So here we see to compute the dredged sediment for the undrained shear strength for the dredged sediment, we use this equation where C sub U is the undrained shear strength, and then we have C sub UI is the initial undrained shear strength. Tangent of phi sub Cu is the rate of increase in shear strength, and sigma prime C is the in situ effective vertical stress. And we can see that we needed to solve for the consolidation stress to use this first equation. So here in our second equation, we have sigma sub V is the total stress due to the weight of the existing soil. U sub S is the pore water pressure. Also, we have so obviously to find the consolidation stress, we needed to find the excess pore water pressure. And so to find this, we used Terzagh's one-dimensional theory of consolidation. And in using this, we assumed the constant coefficient of consolidation CV and compressibility MV. We could assume these were constant because we had a normally consolidated soil deposit. So in this case, it was dredged sediment subjected to levee loads. The pore water pressures were estimated using the principle of linear superposition to determine the excess pressures at different times due to levee raisings.
This paper presented the slope stability results in 5 different steps, which are listed here on the slideshow, and in the following slides to come would be a summary of each of the different steps. So, Step 1, the back analysis of the first slope failure in 1993. They calculated the initial shear strength in the foundation soil layer. They used the Mohr-Coulomb failure envelope to help determine the actual shear strength. Because of the fact that each levee rising stage to the stresses that exceeded previous applied stress, the lab results in this case are not suitable for this stability analysis because samples were or could have been disturbed. For the test they used the triaxial shear test date applied isotropic consolidation stress to effective overburden stress. Basically, this step is about finding the back analysis of the initial undrained shear strength, which gave them the back calculated consolidation undrained failure envelope. The second step, the stability analysis of levees in 1982 to 1989. They use the parameters found in step 1, which helps solve the stability computations for the levee rising in 1982 and 1989, which were successfully raised in both years. The estimate of the undrained shear strength for the foundation soil layer in 1982, 1989, and 1993 were used to predict the slope failure in 1993. Step 3, back analysis of second slope failure in 1993. The stability analysis along with the lab tests were modeled to determine the shear strength of some of the undisturbed specimen from the soil samples. Based on those results, the safety factor was 1.5, which is only the minimum for the undisturbed shear strength of the foundation soil in order for the second slope failure not to occur. But since the pore water pressure completely dissipated in the first failure during the building of the berm, the back calculated shear strength along with failure surface would decrease further. Step 4. Stability conditions following the levee repair in 1993. The U.S. Army Corps of Engineers placed 2 layers of geotextile fabric to reinforce the slope to try to prevent the slope failure again. They were not able to make the levee to 9.2 because the levee started to fail at 8.5. In this case, back calculated remodeled shear strength from step 3 shows that the time to repair the levee rising was halted at the elevation of 8.5. Step 5. Stability conditions following the levee rising in 1995. In 1995, they were able to rise the levee. Based on the results from the stability analysis, and a slope section is on the verge of the failure, had recovered 83% of the initial undisturbed strength. At the time, the safety factor is 1.12. From 1993 to 1995, 83% of the shear strength of the failure of 1993 from 67%. Therefore, they were able to correct the issues that arise during the 1995 failure. This table is the observed computed stability conditions between 1993 and 1995 to make sure the back calculated model shear strength value and the computed pore water pressure used in the stability analysis of after 1993 slope failure, the upper and lower bound shear strength in 1993. For the 2 cases, the 1994 measured shear strength are higher than 1993 but lower than 1995. The main takeaways from this article is that it's important to have a model that accurately predicts the further behavior of the levees constructed over soft soils, as well as it's important to have accuracy of the assumptions and parameters used in the stability analysis.